Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is thermal modification. Thermal. The word thermal is a huge one. We have to understand in various ways. How much we are understanding, it gives something new things. But it's a little word, but it has its own kind of various dimensions are there in this. In this particular thermal modification, we are going to confine in ground improvement techniques point of view only. So in this ground improvement techniques are very essential to enhance the soil properties, making it is suitable for the construction. So we are using n different types of categorizations: physical, chemical, thermal methods. So each method is aims to modify the soil property only, but depends upon the which type of modification is we are required. So in this, for better understanding which are critical for safety and longevity of the structure. So in this, we are understanding in this particular lecture, we are going to understand in thermal modification, innovative approach that leverages the power of heat to transfer the soil properties. Understanding that thermal modification involves applying heat to soil to alter its physical and chemical modification. And their physical and chemical characteristics and whatever the small changes also, it may affect the property of the soil. So it depends. So in this, thermal modification involves to applying the heat to the soil to alter its physical and chemical characteristics. This method can address various soil issues such as high moisture content, low strength and instability, which are common in problematic soil like clays and silt. In this, thermal modification works through two primary mechanisms: physical and chemical changes in the soil structure. In physical modification, drying, sintering are there. In this drying, heat reduces the soil moisture content. We know whenever the soil is have some moisture, we kept into the heat or otherwise the required temperature, it is going to dry, better to dry. So heat reduces the soil moisture content, which significantly impacts its mechanical properties. By drying the soil, its shear strength increases while its compressibility and plasticity decreases. This particular beneficial in stabilizing clayey soils which tend to retain water and exhibit high plasticity. At evaluated temperatures, soil particles can fuse or bond together in a process known as sintering. This results is more cohesive and less compressible soil structure, enhancing its load-bearing capacity. In crystallization, heat can be reduced the formation of new mineral crystals within the soil. These crystals can interlock, creating a denser and stronger soil matrix. This process is advantageous in improving the soil's overall structural integrity. In chemical modification, oxidation and reduction, thermal treatment can change the oxidation states of minerals present in the soil. This can lead to changes in the chemical stability and reactivity, influencing the soil's overall behavior. For example, heating can convert Fe2 plus ion to Fe3 plus ions, altering the soil properties. In decomposition, organic matter within the soil can decompose when subjected to high temperature. This decomposition reduces the organic content, which often contributes the soil instability and compressibility. Phase transformation. Certain minerals undergo phase transformations when heated. For instance, heating can convert kaolin, a clay mineral, into metakaolin, a more stable phase. These transformations can significantly enhance soil strength and durability. Methods. N different number of methods used to apply heat to soil, each suited for different soil types and project requirements. Direct heating, indirect heating, direct heating, indirect heating are the methods. In direct heating, flame treatment, microwave heating. Flame treatment. This method we know, direct flaming to the soil surface. This method involves applying a direct flame to the soil structure. The high temperatures from the flame rapidly reduces moisture content and can burn off organic matter also. It will burn the organic matter also. This technique is typically used for shallow applications due to the limited penetration depth of the flame. This technique is typically used for shallow application due to the limited penetration depth of the flame. Microwave heating. Microwaves generate heat by agenting water molecules within the soil. This method can achieve rapid and uniform heating. In this flame treatment, we are not getting this uniform heating. In microwave, we may maintain the uniform of the heating, making it effective for drying and stabilizing the soil. Microwave heating can be controlled precisely, allowing for target soil modification. Indirect heating, steam injection, electrical heating. In steam injection involves injecting steam into soil, rising its temperature. The steam condenses, releasing latent heat and drying the soil. This method is effective for deep soil applications as the steam can penetrate and heat large soil volumes. In electrical heating, this method uses electrical resistance or induction to generate heat within the soil. Electrodes are inserted into the ground and electric current passes through, producing heat. This technique is versatile and can be used for various soil types and depths. Applications. Thermal modification has diverse application in geotechnical engineering, addressing various soil issues and improving overall soil performance. Stabilization of expansive soils. Expansive soils such as certain clays swell when wet and shrink when dry, causing ground movement and structural damage. This thermal modification gives the solution for such type of problem, that is, thermal modification reduces the soil moisture content and alters the mineral structures of the soil, minimizing their expansion and contraction tendencies. This stabilization is crucial for foundations and infrastructure built on expansive soils. This is the one of the major application which we are going to understand in our stabilization of expansive soils. In expansive soils such as clays swell when wet and shrink when dry. So this thermal modification is one of the application. In remediation of contaminated sites, contaminated soils, especially those with organic pollutants, pose environmental and health risk. The thermal treatment decomposes organic contaminants and violet components, reducing their concentrations and toxicity. This method is effective for site remediation, ensuring safer and cleaner soil conditions for redevelopment. Improvement of soft soils. Soft soils such as silts and pets have low shear strength and high compressibility, posing challenges for construction. Thermal modification increases the shear strength and reduces the compressibility of these soils, making them more suitable for construction purposes. This improvement enhances the load bearing capacity and stability of soft soils. Next one is this permafrost or permeability frozen ground. Permeability frozen ground create challenges for construction in cold regions. Controlling thawing of these permeability frozen grounds using thermal techniques allows for construction activities. By selectively thawing and stabilizing the soils, engineers can ensure a stable foundation for structures built in these particular regions. Case studies and particular considerations. Case studies and particular considerations. Microwave heating for soil stabilization. The overall view. Stabilization of clayey soil for highway construction of the project. We are considering one case study. In that methodology is microwave heating equipment was used to treat the soil inside. The treatment involved heating the soil to specific temperatures to reduce the moisture content and enhance the strength. In results, post-treatment tests showed significant improvements in the shear strength and reduction in plasticity. The stabilized soil meet the required engineering standards for highway construction. Final conclusion, as per the thermal modification, microwave heating provide to be an effective and efficient method for soil stabilization, offering a rapid and controllable solution for the problematic soil. In this microwave heating, uniformity is there. Environment is in that particular soil sample. It is in the same environment. So in this that is efficient for the soil stabilization and also the effective. This rapid and controllable solution for this problematic soil as per the thermal modification. And one more case study, steam injection for contaminated soil remediation. In this overall point of view, remediation of the former industrial site contaminated with volatile organic compounds. In this methodology, stem injection wells were installed across the site and stem was injected to heat the soil and volatilize the contaminants. Vipro extraction systems captured the volatilized contaminants for the treatment and disposal. The results, significant reductions in volatile organic compounds concentrations were achieved and the soil was rendered safe for future use. Monitoring showed no adverse environmental impacts from the stem injection process. It was effective. Stem injection was effective in remediating contaminated soil, demonstrating its potential for large-scale environmental cleanup project. Practical considerations, cost and resources. These thermal modification techniques can be expensive due to the high energy consumption. Cost-benefit analysis are crucial to determine the economic feasibility for each project. Environmental impact. The environmental impact of thermal modification must be carefully assessed. High energy use can be contribute to greenhouse gas emissions, and improper handling of heated soils can lead to the secondary contamination. Soil characteristics. Not all soils respond well to thermal modification. Understanding the specific characteristics of the soil, such as mineral composition and moisture content, is essential for selecting the appropriate thermal technique. Safety. Safety is one of the important parameter in thermal modification. When dealing with high temperatures and specialized equipment, proper training, protective and additions to the safety protocols are necessary to prevent accidents and also the injuries. The safety point of view, we have to take more care when compared to the remaining modifications which we are going to done for soil modification. In thermal modification, it is a powerful and versatile technique for ground improvement, offering solutions to a wide range of geotechnical challenges. By understanding this mechanism and methods, applications, practical considerations, engineers can effectively harness the potential of the thermal modification to enhance the soil properties for construction and remediation projects. This method, when applied correctly, can significantly improve the stability, strength, and durability of the soils, contributing to the success and safety of engineering endeavors. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.